heterocyclic compounds. Heterocyclic just means inside of your ring there exists a molecule that is not carbon. So for example, this nitrogen is what causes this ring to be a heterocyclic molecule. This oxygen right here is what causes this ring to be a heterocyclic molecule. So why do we care about heterocyclic molecules in terms of aromaticity? Well, because they spice things up a little bit, okay? So I have two examples here and we're going to walk through them. So this nitrogen right here, this nitrogen is sp2 hybridized and it has a p orbital. So yes, it has a p orbital. Because, and one reason why I know that is because we have a double bond here, and that double bond, that pi bond, has to be formed using the p orbital of the nitrogen and the p orbital of that carbon. Okay, now this lone pair right here is actually in an sp2 hybrid orbital. Okay, so remember, when we have an atom that is sp2 hybridized, it has 3 sp2 orbitals, okay? So in this case, if I'm going to color code this, so my sp2 orbitals will be orange, this sigma bond is taking part in one of the sp2 orbitals. This sigma bond is being made using one of the nitrogen's sp2 orbitals, leaving this lone pair to be in the last and final sp2 orbital. And then this pi bond is formed using the p orbital. Okay, so I'm going to erase all that because it looks a little bit messy and we have to know what we're doing. But that was a little bit about the orbital layout for that nitrogen. Okay, so how we're going to treat this is we're going to go through our flow chart to figure out if this molecule is aromatic, non-aromatic, or anti-aromatic. So, is it cyclic? Yes, it is. Do we have p orbitals at every atom in our ring? So does this nitrogen have a p orbital? Yes. This carbon? Yes. How about this carbon? Yes. This carbon? Yes. This carbon? Yes. And does this carbon have a p orbital? Yes. Okay. So now I know that my molecule meets the criteria to be either aromatic or anti-aromatic. Now I just have to count the number of pi electrons. So there are 1, 2, 3, 4, 5, 6 pi electrons. Now why did I not count these electrons here? Well, the reason I didn't count those electrons is because they're never in a pi bond. They're never in a p orbital. How do I know that? Because I know that because these electrons are always in the sp2 hybrid orbital that nitrogen has, and we just went over that. So they are never going to be part of the electrons that I count for my pi electron total number. Okay, so if I have 6 pi electrons, that means I need to use the 4n plus 2 rule to use the whole number 1 to get to 6. And whenever I use the 4n plus 2 rule, I know that my molecule is aromatic. So I can label this as aromatic. Okay, let's look at the next one. So this one's a little bit more interesting. So first thing when deciding, is it aromatic, non-aromatic, or anti-aromatic? Is it cyclic? Yes, my molecule is cyclic. Cool. Does every atom in the ring have a p orbital? So does this carbon have a p orbital? Yes, it does. Does this carbon have a p orbital? Yes. And this one, yes. And this one, yes. But does this oxygen have a p orbital? Well, right now it's got 2 lone pairs. So if I count 1, 2, 3, 4, that tells me this oxygen is sp3 hybridized, which means it doesn't have any untouched p orbitals left. They've all been hybridized into the sp3 hybrid orbitals. But you need to remember about resonance, okay? So before I say that that does not have a p orbital, let's see if we have resonance here. So can this lone pair go into a bond, forcing this bond on a lone pair onto that carbon? So the answer is yes, and there's also, a resonance structure going the other way, but I'm not going to draw it. So there is a resonance structure, okay, and looking at the other oxygen, I guess the same oxygen, but in the other resonance structure, what is the hybridization of that oxygen? Because over here, this oxygen is sp3 hybridized, but on the right side, our oxygen is 1, 2, 3 is sp2 hybridized. Okay, so what's the answer? Is our oxygen sp3 hybridized or is it sp2 hybridized? Well, usually when you're looking at resonance and you're trying to figure out the correct hybridization of an atom, when they differ depending on the different resonance structures, you usually pick the lower one. But when we're talking about aromaticity, we're not going to just automatically pick the lower one. We are going to choose what's best for the molecule, what is energetically the most stable choice, because the molecule is going to choose to be the hybridization, doesn't really choose, but if I'm personifying, it chooses to be the hybridization that allows the molecule to be the most stable possible, okay? So, for example, I'm not going to do all of the walkthrough of this, but let's just say, so what I'm saying is, this may or may not be true, but if this molecule ends up being non-aromatic when it's sp3 hybridized, and this molecule ends up being aromatic when it is sp2 hybridized, then what's better for the molecule, to be non-aromatic or to be aromatic? Well, it's more stable for the molecule to be aromatic, so this oxygen would choose to be the more stable version of itself. And so this oxygen would end up being sp2 hybridized so that the molecule as a whole could be aromatic. But if we could have another scenario where, let's say this molecule is non-aromatic, but if it's sp2 hybridized, then this molecule, as an example, might be anti-aromatic. Okay, if that's the case, then what is better for the molecule as a whole in terms of stability? What's more stable, for the molecule to be non-aromatic or for the molecule to be anti-aromatic? Well, it would be more stable for the molecule to be non-aromatic, so the oxygen will stay sp3 hybridized. Okay, so let's look at this one in particular. Okay, so if the oxygen here, let's use another color. Now you have to remember that only the hybrid exists, so resonance is very important. But if this oxygen chooses to be sp2 hybridized, then what will happen? Well, that means that this sigma bond will be in an sp2 orbital, this sigma bond will be in an sp2 orbital, and one of the lone pairs will be in an sp2 hybrid orbital. But that is all of the hybrid orbitals that are sp2. There's only 3 sp2 hybrid orbitals, which leaves this last lone pair to be in the p orbital. Okay? And that's actually, how we would make that pi bond right there, okay? So in other words, these electrons would be counted towards our pi electron number, okay? Along with these 2 electrons and these 2 electrons. So that would be a total of 1, 2, 3, 4, 5, 6 electrons. Okay? Now, if we have 6 pi electrons, which equation do we need to use to get to 6? 4n or 4n plus 2? Well, it's exactly what we did above here. It would be 4n plus 2, meaning our molecule would be aromatic. Okay? So, if our oxygen is sp2 hybridized, then the molecule will be aromatic. What happens if the oxygen stays, as we usually expect it to, be sp3 hybridized? Let's look at what happens then. So if this oxygen is sp3 hybridized, then what is the molecule? Well, automatically the molecule will be non-aromatic. How did I know that? Well, let's go through our flow chart again. So 1, is it cyclic? Yes. 2, does every atom in the ring have a p orbital? Well, sp3 hybrid atoms do not have a p orbital, okay, because they used all of their p orbitals in the hybridization process. And so remember what I said, if you say no to this, automatically you're non-aromatic. Your compound will be non-aromatic. All right, so let's look at our options. If this oxygen is sp2 hybridized, then it's aromatic. If it's sp3 hybridized, then it's non-aromatic. Now, what is better for the molecule as a whole in terms of stability? Is it more stable for the molecule to be aromatic or non-aromatic? Well, the answer is aromatic, because being aromatic compounds are more stable than non-aromatic compounds. So the oxygen here kind of chooses, it's not like these are sentient, but the oxygen basically is sp2 hybridized because it allows the molecule to be in a more stable state. And so this molecule is aromatic. So that's a pretty tough one. So that's why heterocyclic compounds are usually pretty tough. You probably won't get that on the PCAT, but if you're in a lecture class, you might need to know that. Okay, so let's go through and label the following molecules as aromatic, anti-aromatic, or non-aromatic. So here, let's go through our flow chart. Is this molecule cyclic? Yes. Okay. Does every atom in the ring have a p orbital? Yes, yes, yep, and yes. Okay, so that means that my molecule is either aromatic or anti-aromatic. I just have to figure out which one. So how many pi electrons does this molecule have? Well, it's got 1, 2, 3, 4. 4. 4 pi electrons. So how am I going to get to 4 pi electrons? And am I going to use the 4n plus 2 equation or the 4n equation? Well, I'm going to use the 4n equation, which means that this molecule is anti-aromatic. Okay, now this molecule is called cyclobutadiene, and there's actually some interesting debate about if it's actually anti-aromatic or non-aromatic. So if you want to Google that, it's an interesting read. But as far as the PCAT goes, this would be considered an anti-aromatic compound when you follow through with the flow chart and the rules on how we decide if a molecule is aromatic, non-aromatic, or anti-aromatic. All right, let's look at this molecule down here. So, number 1, is it cyclic? No, it's not cyclic. So automatically, this molecule is non-aromatic. Well, that was pretty easy. Okay, cool. Let's look at this one up here. So, is this molecule cyclic? Yes. Does every atom in the ring have a p orbital? So does this carbon have a p orbital? Yes. How about this one? Yes. This one, yes. And this one, yes. And does this carbon have a p orbital? No, because this carbon is sp3 hybridized. We have 2 invisible hydrogens here. All right, so this atom does not have a p orbital, which means automatically the entire molecule is non-aromatic, because we don't have p orbitals at every atom in the ring. So what about this molecule here? Well, is it cyclic? Yes, it is cyclic. Do we have p orbitals at every atom in the ring? Check, 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 check. Yes, oh, and check. Yes. Okay, now we have to figure out, is this compound aromatic or anti-aromatic? So let's count up our pi electrons. So we have 1, 2, 3, 4, 5, 6. 6 pi electrons. So which equation do I need to use? Am I going to use the 4n plus 1 or the 4n? Well, when n equals 1, for this equation, I get 6. So we are going to be using the 4n plus 1 equation, which tells me that this molecule is aromatic. Okay, how about this molecule? Is it cyclic? Yes, it is. Do we have p orbitals at every atom in the ring? The answer is actually no, right? This carbon, this carbon, this carbon, this carbon, and this carbon are all sp3 hybridized, which means none of those atoms have a p orbital in them. Okay, so automatically, since the answer to that question is no, I can say that this compound is non-aromatic. Okay. All right, now let's look at this molecule over here. So is it cyclic? Yes, it is. Do we have a p orbital at every atom in the ring? So we have a p orbital here because we've got this pi bond, and we have a p orbital here. Do we have a p orbital at the carbocation? Well, remember, carbocations have what hybridization? Carbocations are sp2 hybridized. And that's something you should know by now, but if you're still forgetting that, you're going to want to remember that. So remember, carbocations are sp2 hybridized. So yes, this carbon does have a p orbital, and in fact, because it's a carbocation, that p orbital is empty. It's unfilled, it's unoccupied, but it's still there and it still exists. So yes, every atom in the ring has a p orbital. So now we can go through the process of, is it aromatic or is it anti-aromatic, looking at the pi electrons. So we've got 1, 2. We have 2 pi electrons. So which equation do I need to get to 2? Is that going to be 4n plus 2 or 4n? And remember, 0 is a whole number. So we can count n to be 0. And in fact, if n equals 0, then this will equal 2. And that's exactly what we want. Right? This equation will never give us 2 no matter what whole number we use. So that means that this molecule is aromatic. All right, let's look at the next one. I'm changing colors all over the place, but that's okay. So interesting here. We've got 2 fused ring systems. Now, whenever you have fused benzene rings, almost always those fused benzene ring systems are aromatic. But we can go through the same process that we do with any other molecule. And so let's go through the whole process. So, is it cyclic? Yes. Now it's made of 2 rings, but we want to look at the largest ring system that we can that will potentially allow us to have p orbitals at every carbon and count the electrons in the largest ring. So what do I mean? That means that I'm actually going to look at this as our big ring. And that's what I'm going to consider the ring to be. So, is it cyclic? Yes. Do we have a p orbital at every atom in this big orange highlighted ring? Yes, we do. We've got one here, 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 and here. Okay, so yes, every carbon has a p orbital. So now what we need to do is we need to count up our pi electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 pi electrons. Okay, so which equation is going to give us the number 10? 4n plus 2 or 4n? Let's think about this. So if n equals 2, then 4 times 2 is 8, plus 2 is 10. So this equation, when n equals 2, will give us 10. There is no way that this equation, with n being a whole number, will give us 10. So we can just cross that out. Since we're using the 4n plus 2 equation, that means that this molecule is aromatic. Okay, how about this molecule? So you don't want to forget about lone pairs. Just because they're not drawn doesn't mean they're not there. So you need to be paying attention to that. So first question is it cyclic? Yes, it is. Does every atom in the ring have a p orbital? It's interesting because you can automatically look at this carbon right here. That carbon is sp3 hybridized, right? We have 2 invisible hydrogens here, which automatically means that it doesn't have a p orbital, so automatically the entire compound is classified as non-aromatic. Okay, we are getting closer and closer to the end here. So let's look at this molecule. Is it cyclic? Yes. Does every atom in the ring have a p orbital? Yes, right? Because remember, carbocations are sp2 hybridized, which means they have an empty p orbital. So now let's go through and count up our pi electrons. So we have 1, 2, 3, 4. There are 4 pi electrons. Okay, and so which equation do I need to use to get to the number 4? 4n plus 2 or 4n? Well, when n equals 1, I will be using the 4n rule, so not the 4n plus 2. And remember, whenever you use the 4n equation, that means your molecule is anti-aromatic. So that's interesting. All right, let's look at this molecule here. So, when it comes to carbanions, they have resonance, right, throughout the molecule here. So let's draw our resonance structures. And remember, technically only the hybrid exists. So for carbanions, if they have resonance, then that means, and if they can form that pi bond, that means they need to have a p orbital. So, because of that, and there's another resonance. I'll let you guys draw in that other resonance. So that means that I am going to count the electrons in a carbanion as being pi electrons, okay? So, is this molecule cyclic? Yes. And since we have resonance here, we do have a p orbital at every atom in the ring. So the question now is, how many pi electrons do I have? And remember, I'm going to count these. For carbanions, I'm going to count those electrons. So 1, 2, 3, 4, 5, 6. So 6 pi electrons, which would fall under the 4n plus 2 equation, which means this molecule is aromatic. Okay. So let's look at this molecule. Now, we actually have a benzene molecule here, and yes, we have something attached to it, but just because you have something attached onto a benzene ring does not mean that the benzene ring is not there. The benzene ring is still there, and the benzene ring itself is aromatic, even though you've attached something onto the benzene ring. So we would go through this process and we would realize, yes, it's cyclic, yes, it has p orbitals at every carbon in the ring, and we would count that there are 6 pi electrons, and so it would be the 4n plus 2 rule, and this molecule would be aromatic. What I want you to take away from this is, if you have, a group on a benzene ring, it's still going to be aromatic as long as that group is not, for some reason making the benzene ring a different molecule. If you wanted to, you could go through the whole process. So let's look at the next molecule here. So don't forget to draw in your lone pairs. All right, so this is actually the same exact compound that we had up here. And so we'd go through that exact same process again, and we would find that this compound is aromatic. Oops, we don't want to forget this last group over here. So for carbanions, because they're involved in resonance, I always count the lone pair electrons along with my pi electrons if they're on an atom that's that has the ability to do resonance with the ring. So in this case, we can do resonance like that. Okay? So, is this molecule cyclic? Yes. Does every atom have a p orbital? Yes, because remember, this can do resonance. So we can form a pi bond here, which means this carbon needs a p orbital. So how many pi electrons does it have? 1, 2, 3, 4. So it has 4 pi electrons. Okay, so which equation do we need to use to get to 4 for our pi electron number? Well, we'd have to use 4n. And if we use the 4n equation, then that means that this molecule is anti-aromatic.